Thank you so much. Thank you so much for the invitation today, and I'm really honored to be here in this seminar talk. And I know I've made a mistake, actually. I just heard Yujie said that I published many papers, actually. I think that was mistake number one, because comparing to people here, I don't publish a lot. So that's so my name is Song Liu. I come from University of Bristol, and I used to be a student in Tokyo Tech under supervision of Professor Sugiyama. So today I'm really honored to be here and give you this introductory talk about my recent work on statistical inference with time-varying probabilistic and generative models. This is slightly different from the advertised title because I added some ongoing works. So I'll try to be slow today, and if you have any questions, feel free to interrupt me, or if there's any online question, feel free to let me know. Okay, so this talk is based on two recent preprints. The first one has just been accepted by AISTAT 2025, and the second one is also published, is uploaded to arXiv. So I can't do this work without my excellent co-authors, Danny, Leyang, and Xizhen. They were my former students. Yakun is my current PhD student, and Mladen Koller is a leading expert in probabilistic graphical model in USC. And this is Bristol, and I warmly welcome you all to come and visit Bristol one day. It's a really lovely city to work and also live in. This is the University of Bristol, and I work in this building. So it's a really nice atmosphere. Okay, so I just want to give you a brief overview of the things I'm going to talk about today. So basically, there are two halves of today's talk. In the first half, I will introduce the concept of differential parameter learning and a new estimator that was proposed recently called time score matching. And then I'll introduce how to use time score matching to estimate this differential parameter. And then in the latter half of my talk, I'll introduce two applications of differential parameter inference. First one is learning differential graphical model, and the second one is guiding generative models. Okay, so I think you're all very familiar with the concept of parameter inference. So in statistics, parameter inference meaning that you have a probabilistic model P of X theta, where the parameter is theta. And then given a data set D coming from a data generating distribution Q, then you want to estimate the parameter theta in your probabilistic model P. And sometimes not only you want to estimate the parameter, but also you want to quantify the uncertainty of the estimation. There are many ways you can do that. So the classic approach is definitely maximum likelihood estimation. What you can see is that maximum likelihood estimation can be framed as the minimization of Kuebeck-Leibler divergence between data generative distribution Q and probabilistic model P. And then by minimizing the Kuebeck-Leibler divergence, you can find an estimate theta hat. And if you are more modern, then the recent method for estimating parameter is score matching that was proposed by Hivarian in 2005 and 2007. And essentially it works by minimizing this loss function, which is the squared difference between the score function of data generating distribution and the score function of your probabilistic model. So by minimizing this expected least square error, you can find a parameter estimate theta hat. Both of these methods have been very well studied, and you can find their discussions of their properties and applications in existing literature.
Statistics. They were published 10 years ago, a recent matter.
Well, I think, yes, absolutely. I think, by recent, I probably meant like, in recent decades. Thank you very much for the question. Feel free to interrupt me anytime, please. Okay, so what is a differential parameter inference? So to talk about differential parameter inference, we need to introduce a time-varying probabilistic model, P of X theta t. So now you can see the probabilistic model depends on time t. And now the parameter is a continuous function of the time t. And in this case, we have a data set that is generated from the joint distribution x and t. So for each time point t, I have a data point x, and then this is my data set d. So essentially, I want to use this data set to estimate not the parameter theta t, but the time derivative of my parameter theta t, and also its uncertainty.
Is CI integer or real number?
Real number. Yes, real number. Yes, yes, it's a time derivative of the parameter.
Okay. I have a small question.
Yes, please.
So you mentioned that you don't want to estimate theta t,
Mm.
but you want to focus on another function. I wonder why.
Yeah, actually, I will have an application in the next slide. So the overall reason for estimating partial t theta t is that I want to understand how the probabilistic model evolve over time. And because sometimes the evolution of the probabilistic model can tell a lot of information. I will show you an example.
Yeah, but
Yes.
But if you estimate theta t, or if you know theta t, you can obtain partial t theta t. But if you have partial t theta t, you cannot recover theta t. That's my point. I wonder why.
Yes, yes, exactly. So this is exactly like estimating density ratio, but not estimating the density separately. So essentially, I want to know. Yes, yes. So the only thing I want is partial t theta t. So that's the target of my learning objective, right? Okay. So we have a few assumptions. Hopefully, it's not too strong. Theta t is smooth. It's depending on application, then you can define different kind of smoothness. And this is different from change point action setting where theta t jumps suddenly before and after the change. In this case, we consider a smooth theta t. And we also consider the data general distribution Qx given t belongs to an exponential family distribution. And in this case, the distribution comes from this exponential family of models, which have natural parameter theta and sufficient statistics fx. So here, probably it's not very clear, but it's theta star t. And we make no assumption on the normalizability of my probabilistic model, which means that it might have a normalizing constant, which is the integral of the unnormalized part. This can be difficult to compute. And not assuming normalizability is very important because it allows us to consider a wide range of exponential family models. For example, we could use pre-trained neural networks as the sufficient statistics f of x. Okay, is the setting clear? Okay, cool. Okay, so I just want to give you a quick example on why do I care about this differential parameter. So the reason that I care, because in a lot of real-world applications, the partial t theta t, the differential parameter, describes how things change over time. Imagine in this SIR model, which is widely popular in epidemiology, you have the following parameters: ST, IT, and RT. So they represent susceptible individuals at time t, infected individuals at time t, and recovered individuals at time t. But this model doesn't focus on the parameters at certain time point t. Instead, it describes the evolution of these three parameters. And in fact, it defines the evolution by using a set of differential equations on partial t st, partial t it, partial t rt. So understanding how these three parameters change over time could tell us a lot of information about how the disease spread in the population. Okay, but this is just a kind of illustrative or toy example. I didn't do any experiment on this on this application. I just want to use this application to show why, in some cases, we are interested in the differential parameter, partial t theta t, because it describes how things change over time. And in many cases, it is the most valuable information that in the application. Okay, so next, I want to talk about some methodology that was a method invented in recent years. By recent, I meant recent, 2022. and it is called time score matching. So to understand what is time score matching, first we need to know what is time score function. So time score function is essentially, so given a time varying distribution, qxt, and in this case, it's a conditional distribution, qx given t, the time score function, st, is the time derivative of the log density function. So it's partial t log qt. So this is the time score function, and it characterizes the change of the log density of q with respect to time. And in fact, the reason I'm very interested in this time score function because it has a close relationship with density ratio function that I used to work on. You can see easily that the log density ratio between qt1 and qt2 could be written as the difference between these two terms, and then this difference could be rewritten as the integral of the partial t log qt from t1 to t2. Sorry, here is a typo, t1 to t2. And that is why the time score, st, is sometimes referred to as the infinitesimal density ratio, because it characterizes the change of distribution in a very small amount of time. And then if you integrate over this infinitesimal change, you get the proper density ratio. And that actually is the reason this time score function was proposed in a 2022 paper. And you could also consider this discretized expression, essentially just to break down the ratio in terms of a sequence of sum. And that is log qt1 divided by qt2, qt2 divided by qt3, and sum all the way to log qtn minus 1 to qtn. Then if you sum all these up, then you recover this log density ratio qt1 divided by qt2. So this is just a discretized version of the infinitesimal density ratio earlier. Okay, so back to the time score function. So in this case, how can we estimate this infinitesimal density ratio function? First, we introduce a model. This model is called st of x parameterized by phi. And then the time score matching is easily, simply just the squared difference between the true time score function st and the model time score function st phi. And by minimizing this squared loss, we could estimate our model st phi, and this model st phi is the estimated time score function. Here, I have another function g. This g is a weighting function, generally kind of a positive weighting function. I'll talk about it later. And this st phi, which is the model for my time score function, is usually a neural network model. But you can see that this least square problem is not tractable, directly tractable, because although we do know the model st phi, but we do not know st of x, which is the true time score, because recall the true time score is partial t log qt. So this is different from the regular least square regression. And in this case, you don't know the target value, the true time score function. Then what do we do in this kind of situation? So yes.
Small function. What's the dimensionality of st of x? The score.
Oh, so it's one dimension. Sorry, it's one dimension. So it should be like just a square bracket. Sorry. Yeah. Sorry. Thanks very much. Okay. So if you are familiar with the regular score matching, then you must be familiar with this integration by parts trick. That integration by part trick is essentially applying the integration by parts to the cross term of this least square objective. And then you will get the same square term, but the cross term now becomes the integral of this expectation of partial t gt times st minus two expectations. And these two expectations are expectation evaluated on qt max and qt min, t max being the biggest time point I have, t min being the smallest time point I have. And these two expectations comes from the boundary condition when applying the integration by part trick. and then followed by some constant that doesn't depend on my model. So the first thing you'll observe is that these terms are all expectations. So if you have sample from Qt, Qx given t, then you could easily approximate all these terms with sample average. And then this intractable objective function becomes a tractable objective function that can be approximated using samples from Qt. And here, so just a small notation here, G overline and G underline are just the GT max and GT min. And actually, you could also eliminate the boundary terms by setting the weighting function GT min and GT max equals to 0. Essentially, you just kill off these two terms. And that makes the overall loss function a little bit simpler. And if you do that, then this time score matching is a special example of truncated score matching because you are matching the scores over a truncated time domain from T min to T max. Okay, so that's the objective of time score matching. Then by minimizing this objective function, you can obtain an estimate of the time score ST phi. Okay. So is this time score matching clear?
Another very small question.
Sure.
So maybe I have two questions here.
Sure.
So you just mentioned that the G is some weighting function. So
yes.
That function is chosen based on some applications.
Yes,
problem.
exactly.
So you can put some assumption you want. Like
exactly.
GT max and GT min are all 0.
Exactly. Yes.
Okay.
Correct. Yes.
So do you have other assumption on it?
It needs to be positive, and I think that's it. I think it cannot be unbounded, of course. It cannot have infinite derivative like it is. It has to be smooth in some sense.
Okay, Lipschitz continuity.
Yeah, exactly. Lipschitz continuity.
Okay.
Yes.
Okay. Then another more practical question. So I noticed that in your objective function there is the first term as the square of the model of the time score function. And,
yes.
And that can be. I mean. In some cases, if the model is very complex, if you have the score of the model,
right,
the second term is fine.
Yeah.
And you eliminated the third term, but minimizing the first term can be unstable.
This could be unstable because if the score function, the score model is very, violent, like it is not Lipschitz continuous.
I mean, even if it's Lipschitz continuous, if it's contains some very deep neural network inside it. If you have square, it can be very unstable. If you have a very if you have a frozen deep network as the feature extractor, and you have a linear, oh, maybe that's the case.
Yeah, exactly. Yeah, because
you only learn the
last layer. Yes, exactly. Exactly.
Okay, that would be stable.
Yes,
okay.
Yes. But in the original paper, Choi et al. 2022, they did propose this objective, and their model is a neural network. But in our research, we only estimate this shallow model. The last layer is.
But for that one, the original version, the optimization can sometimes be very unstable.
I see.
Because you square a nonlinear model.
I see. Yeah, that's a. Yeah,
it depends. You need to very carefully choose the optimizer and tune the learning rate schedule. VDK something.
I see.
Otherwise, if you have a very complex nonlinear model and you square it, it can be sometimes unstable.
Yes.
But that's not the issue of the objective. That's the issue of the optimization algorithm.
Yeah. That's interesting.
That's a big headache in our research.
I see. I definitely, let's talk about it more in after the.
Okay.
Yeah. I think it's a very interesting observation, and actually, in the later half of the talk, I will talk about time score matching using a neural network. I think that's a very interesting insight. Thank you very much.
How did you handle the integration of D?
Oh, integration. I see. So essentially, okay. So because this Qt is a conditional density function qx given t. And if you assume the time is uniform, then essentially that you have a joint expectation over the joint distribution of x and t. And then if you have the joint expectation over x and t, then you can use the data set, which I assume that we have the joint samples x and t to approximate the expectations.
That's wrong assumption.
Yes, it is, I think. But yeah, in the case that if the distribution of t is not known, in this case, we always assume it's uniform. So we always assume it's uniform. But if it is not uniform, then we need to also.
Well, can it become GT as a normalized density?
Yeah, I think so. Yeah, I think you can merge both of them, like the weighting function and the density function of t. Exactly. Yeah. Actually, later I'll show you an example where GT sort of does that in a way. Okay, so now this is the time score objective function, and you can minimize the time score matching objective function to obtain an estimate of the time score. Okay, so I want to talk about next is the differential parameter inference. That is, how do you use the time score matching objective to estimate differential parameter? Recall that the differential parameter is partial t theta t. So in this case, we assume an exponential family model, which means the q of x given t is in this family of distributions. We have a true parameter theta star, and we have a sufficient statistic f of x. Then if you calculate the time score function for this family of models, you'll see something interesting, because the time score function takes a special form. That is the inner product between the differential parameter partial t theta t, which is the true differential parameter, and the centered sufficient statistics. And this is the inner product between the true partial t theta t and the centered sufficient statistics. Has a nice linear form. And the important thing here is that it only depends explicitly on partial t theta t. That is the exact target we want, the differential parameter. And this also does not contain any normalization term. So you can see the z doesn't appear here. Okay, so it's an inner product, depends only on the differential parameter. And this is the inspiration of our time score model. So this, in this case, we create a model for this kind of time score for exponential family models, STX partial t theta t. And the definition of this model is given as follows. So it is an inner product between the partial t theta t and the centered sufficient statistics. And here, partial t theta t, I don't go into detail for now, but you can just imagine this is some function of time that I'm going to estimate later, okay? And the important thing about this time score model is it only depends on the partial t theta t, the differential parameter that I'm interested in. And you can see that by plugging in the true differential parameter partial t theta star t, then we recover the true time score model, the true time score, sorry. And then the rest is, yes, QT, yes, yes.
But in practice, you only have one sample.
Ah, yes, yes, exactly. So in this case, that I will have to approximate that term. So using some kind of kernel smoothing estimators. Yes. So actually, this is not exactly the model I use, but I'm going to approximate this model later using the smooth estimator, kernel smooth estimators. Yes. And okay, so now we have this time score model for exponential family distributions. Then we could just plug it back into the time score matching objective function. Then we will have the following loss. And by minimizing this loss function, we will get an estimate of the differential parameter. Because the true differential parameter is a minimizer of this loss function, then by minimizing this loss, under mild conditions, I could get an estimate of my differential parameter, partial t theta t.
do we need some realized assumption for this minimizing?
Yes, exactly. Yeah, so under some mild identifiability assumptions, then we could obtain an estimator of the partial t theta t.
Bregman divergence
Bregman divergence of sorry.
instead of the square Euclidean distance.
Yes. So I also thought about it, but so far I haven't found a solution because the square is essential for integration by parts trick. So then you have the cross term, you can apply the integration by parts trick. Otherwise, you can't. For example, if you replace it by like a log or like a Kubeck-Leiber-ish, then you can't have the integration by part trick. Yeah. Any other questions? Okay. All right. So then, similarly, we can apply integration by part trick to transform this intractable loss function to a tractable loss. And the idea is, again, like by expanding the squares and then replacing the cross term using integration by part trick. Then we'll see again we have this we have this square term. Then we have this cross term now become something like this. So in this case, I eliminated the boundary terms because I assume GT is 0 at the T max and T min. And then I end up with this kind of cross term. Again, everything is in an expectation. Then you can use samples, the joint samples from X and T to approximate expectations to obtain a sample version of this objective. Then minimizing this empirical version of the objective, we could obtain an estimate of the differential parameter. Okay, so that's the methodology so far. We introduced.
Ask a question before
Yes.
you go.
Yeah, sure, of course.
I have a question from the beginning of your talk.
Right.
So in the very beginning, you have a distribution of, or maybe a model of X, right? X
Right.
is a random variable, and
Right.
you have a P X
Right.
parameterized by theta. And
Yes.
then you want to make this model to be time dependent, and then you have a theta T.
Exactly. Yes.
And then why is T a random variable? Because to me,
That's
you have X is a random variable and X has a distribution, and you want to make this distribution to be time dependent, and then you have T.
Yes. Yes.
But you also mentioned that you don't know the distribution of T, so you have to regard it as a uniform distribution.
Right.
But to me, T is not a random variable.
Yes,
at all.
yes, absolutely. Yeah. So the reason that T is not a random variable, well, the reason I said like we assume it kind of uniform is because I could then use the joint samples X pair T to approximate those expectations.
So only technical reasons.
Exactly. Yes, exactly.
Okay,
For
thank
technical reason. Yes. So yeah, in this entire research, actually, we only regard T as a uniform distributed T. But yeah, in fact, we really don't care that much about the distribution T. Sorry.
I think there's some question from the online chat.
Yes.
So why it is not a direct application of choice results?
Right. So okay. So probably the reason I'm saying this not a direct application is that because in the model that you can see, not only I have the differential parameter, but I also have a center sufficiency thesis, and this expectation is also a function of time t. So if you apply integration by parts, you will have to take care of this function of time t as well. So like in the general sense, this is another term that you need to somehow transform to get a tractable form of the objective functions. So basically, instead of integration by parts, we need to apply integration by part twice to eliminate this undesirable term in the cross term. In the cross term, I don't. Is it okay?
Yes. So if the analyst has any question, you can just
Okay, cool. Thank you very much. Very good question. Very good question. So, okay. So let's move on to some applications. So the first application is learning differential graphical models. This work I have done in the past before when I was supervised by Professor Sugiyama as well. So in this case, let's consider a pairwise graphical model. And graphical model is basically a special case of exponential family, and it can be parameterized like this. So you can see I put parameter on each pairs of xi and xj. So essentially, I have a graphical model describing the interaction between random variable xi and xj. So this parametric model you can see is a very expensive model in the sense that the number of parameter grows quadratically with dimensionality. And therefore, we need to use some kind of regularization. We need to introduce some kind of regularization on the parameter theta. And the most popular regularization is L1 regularization, so lasso regularization. Then we can get a sparse estimate of theta. Then the sparse estimate of theta helps us to construct a graph, a sparse graph that describes interactions of random variables. So this can be a really useful tools in real-world applications. So the setting is that we have a set of samples from data generating distribution QX, then we could just apply maximum likelihood with this L1 regularization term to obtain an estimate of theta, which is theta hat. So this procedure is called graphical lasso. And L1 regularization helps us to get a sparse graphical model. Okay, so now let's consider time-varying graphical model. So time-varying graphical model could be also very useful in time series analysis, right? You are describing a set of graphical model moving in time, evolving in time. In this case, we have a probability distribution, probabilistic model, px theta t. Again, theta is a function of time. And you can, again, optimize or estimate this model using maximum likelihood over all the time points t. But now you also have to regularize for all the graphical models at all t. So that's why you can see there is a sum in front of this L1 regularization term. But a more common learning objective in the literature is this fused lasso regularized learning objective or multitask learning objective, in which case not only I have a L1 regularization on theta t, but I also regularize differences between theta t and theta t prime. And in this case, I introduced an additional assumption. This additional assumption is the differential parameter is sparse, in addition to the parameter themselves being sparse, because now I have two regularization terms, and one of them regularizes the change between graphical models at two different time points, t and t prime. So that's the existing work on how to learn this time-varying graphical model. But recall, our target is to learn differential graphical model, which is the partial t theta t. And we also want to borrow the earlier assumptions where the change of the graphical model is sparse. And in our case, it's just partial t theta t being sparse. And of course, one thing we can do is apply the existing method estimating this time-varying graphical model for each individual t. Then I compute the time derivative for theta t. So first estimate theta t, then I compute partial t theta t. But this requires an unnecessary step of estimating theta t. Can we directly estimate partial t theta t and regularize partial t theta t using one short objective function, a single objective function? The answer is, of course, yes, because I've been talking about time score matching objectives. So you can just use the time score matching objective function with an L1 regularization applied on partial t theta t to obtain an estimate of the differential parameter, which is partial t theta t. Okay, and this gives you an estimate, a sparse estimate of the time differential, differential graphical model. Okay.
The previous method, so only two neighboring graphs are considered, but now you have a series of graphs over time.
Yes, exactly.
So you are assuming smooth change, so not only two.
Exactly. Exactly. Yes. Yes. Exactly. Yes. Okay.
May I know the motivation for estimating this partial theta star, since It seems the goal is to have a sparse theta star.
Right.
Even if the partial
Right.
theta star is sparse, but the theta star is not sparse, I think.
Exactly.
Yeah.
So this is a very good question. Actually, I want exactly that. I want to estimate the sparse change, even if the graphical model themselves are not necessarily sparse. For example, in some biological application, the genes are connected very closely, so you have a dense graph. But the change of the gene over time is simple. So basically, I want to capture that simplicity in a complex graphical model. Yes.
Thank you.
No problem. Okay. So, okay, I will quickly go through this because this is just the empirical version. So in order to solve this score matching objective, we need to translate the population version of the objective to an empirical objective. And in this case, assume we have paired samples X and T from the joint distribution, then I could just approximate all the expectations in my previous population objective using sample average. Oh, sorry. And then here you've noticed that I replaced the ST with S hat T for exactly reason that Professor Sugiyama was talking about, that I have an intractable expectation here. Sorry, I have an expectation here with respect to QT. So now I must obtain an estimate for this expectation. And in this case, I replace this expectation with a Nadaria-Watson estimator using my data set. So essentially, I am using an approximation of my model ST in my objective function instead of just ST.
So if you make the kernel bit very small,
yes,
can you somehow recover the previous method of considering only 2 time points?
Ah, that's interesting. I've never thought about it. Yeah, that's an interesting thought. I have to look into this. My feeling is not because this is a quadratic form. Our previous method is like a Quebec library motivated objective, so probably a bit difficult. But I think, yeah, maybe after some mathematical manipulations, we could get something very similar. Yeah. This is a very interesting insight. Thank you very much.
For the 2 time point case,
Yes.
I think you can use the regular divergence on this.
Exactly. Yes.
The last
Exactly.
This can be somehow identified by looking at the special case of.
Looking at the limit case, I see. Looking at the limit condition of the kernel. Yeah, it's interesting. Yeah, definitely. Yeah, I'll have a look at this later. Okay, so any other questions on the objective? Okay, so final point before I go into the experiments, I want to mention how do I model this partial t theta t. So I mentioned like partial t theta t is just kind of function that I'm going to estimate in the objective function. But here I give you 2 concrete examples. First one is a linear model. In this case, I assume theta t is just a linear function alpha times t, which means the parameter changes linearly over time. Then the partial t theta t is just a constant parameter alpha, right? And the second more fancy model is the Fourier series model. I assume theta jt, the jth component of theta, adopt this Fourier series. Then partial t theta t looks like this. So again, it's just the Fourier series, but sine becomes cosine, cosine becomes sine because of the differentiation. And this model is suitable for periodic variations. And this is suitable for linear changes in parameters. And in this case, in the experiment I'm going to show later, I only consider this linear model because this linear model actually gives us a very simple objective function, because if you apply the linear model, you'll see the quadratic objective function becomes much simpler. That essentially I have a quadratic term here with respect to these covariance of my sufficient statistics, and the linear term with respect to the expectation of the sufficient statistics with an L1 regularizer directly applied on the parameter alpha. And this kind of objective is simply a quadratic programming with L1 regularization. Easy to analyze, easy to optimize, and easy to kernelize. Okay, so it's a very simple objective function if you use a linear model. I will quickly go through the theoretical result without talking too much. So here, I I'm just saying that this result shows alpha hat is consistent, meaning that we have this error upper bound for estimating the true differential parameter alpha star. Recall that alpha star is the true differential parameter if you assume a linear model. And the upper bound depends logarithmically on the dimensionality of theta, which means it is suitable for high dimensional settings. And it also depends on the L0 norm for the partial t theta t, which is the number of non-zero components in the differential parameter. And this is good because it only depends on the non-zero pattern, the number of non-zero elements in the differential parameter, and does not depend on number of non-zero elements in the parameter theta t, which means that even if my individual graphical model theta t is not sparse, the estimation is still well behaved.
May I have a question?
Yeah, sure.
Which the t is for? So I think the theta, partial theta star for is different for each t.
Oh, right.
Yeah,
so actually,
which t here?
that's a good point, actually. Sorry, I should have clarified this. So actually, I'm assuming a linear model. So essentially, it's just the non-zero number, non-zero
So
number.
it's the
Yeah,
same.
exactly. Yeah, it's the same. Yeah, thank you very much.
So can you extend your analysis to, for example, like the Fourier, the model, or
Oh, yes.
other general kinds of?
In theory, you can, because here I have just a lasso regularized objective. If you change to Fourier series, then you have a group lasso regularized objective. So similar theory do exist for group lasso as well. You'll get similar results. Yeah, but in like a grouping way. Right. Okay, so now have a look. Let's have a look at a few. Oh, right. So in this case, we just fix it to 0.1 in experiments. And so in the theoretical, okay, I see. So in the theoretical analysis, we didn't consider the Nadara-Watson. We are considering that using the true model, using the true score model. So this is the reason that the bandwidth doesn't enter this theoretical results. But yes, if you want the theoretical result to be consistent, then the bandwidth must shrink to 0 as we have more and more observations.
Can you use the validation data?
Actually, it's well, yes, I think you can, but this is a bit strange because we have essentially like a weighted least square objective functions. So essentially, we are choosing the weights based on some kind of cross-validation errors. I think yes. So okay, I see. So yes, we didn't do that, but I think if we just use like the testing error for this time square matching, then we could choose the bandwidth for the Darrell-Watson estimator. But the situation is a bit complicated because in time series it's not IID, so cross validation is not valid. Yeah, but yeah, if we could derive some kind of like testing error.
The final bandwidth constant over OP.
Right.
Maybe like at some point change of the parameter is very high.
Exactly. Exactly. Actually, we were like when we were writing the paper, we were considering this kind of local linear model that basically we estimate, using a time window essentially for the entire time series. So inside of each window, we have like one bandwidth, and then we have different bandwidths for different window. And then for each window, we could apply some kind of testing, like holdout validation for choosing the best bandwidth for the Nadara-Watson estimator.
Is it critical?
We just use like 0.1 to seem to work well for our experiments. Yeah. Okay, so let's have a look at some experiment. So first I want to give you two visualizations. So these are two visualizations of partial t theta t versus theta t. So on the left, you have estimation for partial t theta t. On the right hand, you have the estimation of theta t. So essentially, this is our method, and this is an earlier work for estimating the time-varying graphical model. So on the left, you can see that it's a very clean plot. I highlighted all the changing parameters using the red lines. And you can see that other than these red lines, our estimator picks up no signal, which means all the other parameters are penalized to 0 thanks to the lasso regularizer. On the right-hand side, I also highlighted all the changing parameters, but you can see it's a lot more noisy because I have a lot of things going on in the background, and those background are parameters that doesn't change over time, but because they are still part of your probabilistic model, so you still have to estimate them using existing methods. So that is why you see the plot is a lot more messy than our method. And if I don't tell you which one of the parameter is changed, which is usually the case in application, then you probably have to dig through all the estimated parameters, theta 1, theta 2, theta 3, and see which one of the parameters or few parameters are changing. So that's the difference between theta t and partial t theta t, okay, in these experiments. And here I also have a real-world application, which is a kind of a differential graphical model describing the voting pattern of the US Senate. And in this case, I plotted the differential graphical model in this plot, each edge meaning there is a non-zero partial t theta t. And for positive partial t theta t, I have this red line. And for negative partial t theta t, I have blue line. But you can see there is no blue line on the plot, which means that all the edges I have recovered are positive edges. What do we mean by positive edges in this case? It means that two senators are getting closer and closer over time. So for example, if I have a red line connecting this senator and this senator, then meaning that over time, their relationship is getting closer and closer. So the data set are just all the voting records in the 109th US Senate. And you can see that the pattern that we have discovered are, this kind of affinity groups forming during this congressional session, and the people in the same party are getting closer and closer, forming this kind of voting bloc, while we don't observe any meaningful cross-party or bipartisanship between two parties. So the blue ones are Democrats and the red ones are Republicans, and we don't see any bipartisanship forming during this congressional term. And this shows that the US Senate is getting more and more partisan over this congressional term. Okay, so I realize I have limited time, but I don't want to go too much over the time. I want to check with the chair. Is it okay for me to continue for the next application?
Yeah.
Okay, so just let me know if I'm running out. Yeah, okay, cool. Okay, so in the next application, I want to quickly go through is ongoing work for guiding generative models using time-square matching. So I'll skip the general introduction of generative model because I think you all know what this is. Basically, it is x equals to gz, where g is a neural network, z is a reference random variable drawn from distribution pz. And then by applying this g to z, you get a high-dimensional sample x. But in recent years, a lot of methods like GAN, VAE works in that way. But in recent years, people are more and more interested in time-varying generative model, like diffusion model, like flow matching. So these kind of generative model have an interesting expression that xt equals to gzt. You see that the generative model depends explicitly on the time t, and t is a continuous variable here, which means that if you choose different t, you get different sample. So instead of generating sample in one go, then you generate samples iteratively, progressively. And in this case, this generative model can be seen as an ODE or SDE solver with these parameters. So x0 is the initial condition, and this condition is sample from the reference distribution. And t, the target time, t sol, target time is at time t, and the velocity field is v. And in this case, the velocity field is usually a neural network trained using some kind of criterion, like minimizing Kullback library divergence or preserving some marginal distribution, like a rectified flow. Okay, so by solving this ODE at different target time, you get different time varying generative models, time varying samples, XT. Okay, so the entire generative process is a time varying process with respect to T. Okay, this kind of generative model works great in practice, but its training is very challenging. It requires a lot of samples, and it also is very computationally expensive, and solving this ODE is not easy as well. So a lot of computational hurdles. Okay, so let's have a look on how do we optimize a statistical model or probabilistic model in traditional way. So natural gradient descent is a very popular method for optimizing a statistical model, not a generative model, but statistical model. Suppose you have exponential family model Q x theta defined in the same way earlier with a sufficient statistics f of x, then the natural gradient descent is defined like this. Essentially, you have f inverse times the ordinary gradient with respect to the loss function L. Okay, and this f is the Fisher information matrix. And the Fisher information matrix for exponential family model takes a special form, that is the second order derivative of the log density function Qx. And if you expand this, you end up with just the covariance matrix of the sufficient statistic f of x. So that's a special case of Fisher information matrix. And this natural gradient descent depends on the Fisher information matrix F, because I need to compute F inverse times the regular gradient. Okay, so natural gradient descent, as I said, is a method for optimizing a parametric model, parametric probabilistic model, but it's also difficult to implement in practice because you can see the Fisher information matrix F here is a covariance with respect to the model distribution Q theta, unless for some very simple Q theta, this Fisher information matrix is generally intractable, right? So, okay, now we have two things. One is generative model, works great in practice, and the other is natural gradient descent, works great in theory. Can we combine these two things together and find a new way training a generative models? So this is a brief illustration of the idea in this ongoing work that's called natural gradient descent guided generative model training. So the key idea is that given a time varying generative model, xt, we project its evolution onto the manifold of exponential family. Then we align the projection with an actual natural gradient descent step. So here is an illustration. Suppose at this point, time, okay, gt, the output distribution of my generative model is qgt. Then taking a small step in time, I get qgt plus epsilon, which is an infinitesimal amount of time. And then the difference between these two log densities is naturally just the time score, right? It's an infinitesimal change of the log density, therefore it is a time score. And you can see the time score matching allows us to project this time score onto the manifold of the exponential family, and that is the delta I'm visualizing here. Now, because my generative model hasn't been tuned, so the direction could be pointing different directions here or there. But what I want to do is to align this projection with a natural gradient step by minimizing this dotted line. So essentially, I want to align this projected change with the natural gradient step. So to do that, I have two steps. So the first step is that I'm using the time score matching to find the projection from this time score to the parametric space. Because, as I said, we have restricted ourselves to, the manifold of exponential family. Then the time score model takes this specific form, which is, exactly the same thing I saw earlier, inner product with respect to the differential parameter and the centered sufficient statistics. And this is the true time score. By minimizing this objective function, we get delta, which is a vector in RD, in the parametric space, that characterizing the infinitesimal change in the generative model at the current time. And in fact, this delta, this infinitesimal change delta has a closed form solution, because here I am using a linear model for theta t. Therefore, I'm essentially solving a quadratic programming problem. Then I end up with a closed form solution that looks like this. And you can see that this closed form solution can be rewritten using reparameterization trick, so that I can approximate these two expectations in the solution using samples from my generative model. So essentially, I don't really need to solve this. I just need to, approximate the solution directly using samples from my generative model, which I have at all time t, right? And now you can also see that this projection in the parametric space, delta is also a function of w, because apparently, the G function generator depends on the neural network parameter w. Therefore, of course, the projection depends on w as well. Okay, so that is the projection, step one. And step two is to match that projection delta with a natural gradient step. And by solving this minimization of the squared error. So essentially, I'm just minimizing the L squared distance between natural gradient step and the projected vector delta. So here is a summary of my algorithm. At time t, I first sample a batch, and then I approximate the natural gradient and my projection using samples from my generative model. Then I minimize the objective number one. And then I move on to the next time point and repeat on and on until finally the model converges. Then I get the parameter w as the parameter of the final generative model. Okay, but you can see that this is very time consuming to solve this kind of minimization problem iteratively at every step. So in practice, we propose two particle-based methods without actually solving this least square minimization problem. But I'll skip that for the sake of time. Directly jump into some results. So essentially here, I have this illustrative example comparing the implicit natural gradient descent, which is our proposal, with the classic natural gradient descent. And each circle represents the 95% confidence interval of a Gaussian distribution optimized by natural gradient descent. And you can see they behave almost identically. So you're not losing much in this two-dimensional example, that doing our implicit natural gradient descent is almost the same as doing the ordinary natural gradient descent. And we also compare the convergence speed for different particle generative methods. We compare our implicit natural gradients. The first two are our methods with Wasserstein gradient flow and MMD flow. So both of Wasserstein gradient flow and MMD flow are particle-based generative training algorithms. And we see how fast do they converge to the target distribution. So of course, like the lower, the better on this scale. And you can see our method is significantly better than the other two particle-based methods. So these two are different dimensions. This is 5 dimension and this is 20 dimension. I'm only showing 20 dimension because if I increase to like 50 dimension, then all these 3 lines will just blow up. But actually, surprisingly, this red line, which is a variant of our method, works quite nicely, even with like 50 and 100 dimensions. And we also tested on a covariate shift data set, that is by transporting the target sample to the source distribution by minimizing the Kubeck-Leibler divergence using our implicit natural gradient descent. and compare with two other particle-based methods. And you can see our method has the largest performance gain comparing to the other. Oh, so number. So here, the first column is the base performance. That is using the source classifier directly on the target classifier, which is supposed to be bad without any covariance shift adaptation.
Test accuracy.
Yeah, test accuracy for the source classifier. And so basically all these are just the performance gain or loss after you transport the target sample to the source domain. And therefore, of course, like the bigger the number, the better, right? And our method gives consistently a better result comparing to the other two methods.
Initially, the motivation was to make the optimization faster, like in the previous case.
Right.
Next case.
Right.
In the covariance shift case, you are saying the performance.
Yes. So that's a good point. Actually, I think what happened is that our method is like more robust comparing to other methods in this setting, because I think this has like a 100 dimension or something. So it's a really high dimensional setting. And for these methods, like Wasserstein gradient flow and MMD flow, it takes really long time for them to converge, or sometimes just don't converge at all in such a high dimensional setting. So I think what we are seeing here is more like a high dimensional version of these two plots. But I think like only like our method converged to a nice result. But for the other two, they kind of failed. They kind of like not converging nicely. So in this case, I set the step size to be, as big as possible, without leading to some numerical instability. So yeah, so I think that's maybe what is happening.
You presume that all methods was the same solution, same kind of solution.
Yes, exactly.
Is it really true?
Yes. So in this case, like, so for our method, like natural grade descent, we're minimizing the Kubeck-Leibler divergence, so it should convert to the target distribution. For Wasserstein gradient flow, it's also minimizing Kubeck-Leibler. For MMD flow, so I think for all methods, they all sort of converge to the minimizer of their loss function. And for us, it's like Kubeck-Leibler. For them, I think it's like reverse Kubeck-Leibler and MMD loss. So in principle, yes. That's a very good point. Yes, exactly. So in this case, I use a non-parametric model, which is a particle-based method. So basically all methods here are using kernel one way or another. Like MMD, they use the kernel to approximate the MMD. Wasserstein, they use also the kernel to approximate that gradient.
So because all the loss objects are based on some divergence measure rather than semi-divergence. So
yes,
if it converges to zero, then that means you recover the truth.
Yes, that's a good point. Yeah, that's a good point. Actually, I didn't. So I was hoping that, I could somehow compute the divergence and plot it here as well, like supplement to the MMD. So here I'm just plotting the MMD, but I was hoping to plot some kind of a Kubeck-Leibler divergence here. But because the dimension is very high, Kubeck-Leibler is not stable at all. So you get like very crazy behavior of the Kubeck, like numerical Kubeck-Leibler divergence. So yeah. I think that's absolutely correct. That yeah, I think if you are using different kind of model, then even if you use neural network model, you probably don't get exactly the minimizer of the Kubeck-Leibler divergence.
But the optimization is convex?
Optimization? No, not exactly. So the score matching is convex, but I need to do this kind of matching to the natural gradient every step. And that makes the overall problem non-convex at all. Yeah. Is it convex for minimizing Kubeck-Leibler?
Even if this is convex, you do this, you don't draw to convex.
I think this, well, even if this is convex, I'm like solving the convex problem at each iteration. So, the overall result might not converge to the global optimal solution.
Maybe it's a bi-level optimization problem.
Yeah, exactly. This is a bi-level optimization problem. So yeah, so the best we can hope probably is to reach some kind of stationary point. Yeah. Yeah. So unfortunately, like for this ongoing work, we don't have any theoretical results yet. So we don't know, what is the theoretical result, like theoretical performance of the proposed algorithm. So this kind of algorithm.
God, diffusion mentioned in the first page.
All right, sorry. Oh yeah. Yeah. I think for GAN, yeah,
Forgot God, just diffusion.
diffusion models. Yeah,
Very challenging.
exactly. Yeah, exactly. Yeah. So so this is still ongoing, but one thing I'm trying to do in the future is that I'm going to, like introduce a very specific sufficient statistics F, because in our model, you need to choose the sufficient statistic F. So in our case, we just used kernel models. But I think if you choose some kind of more informative sufficient statistic F, it's possible that we could speed up the convergence of the method. Because it's kind of like a mixture between, traditional parametric optimization and the generative model optimization. Hopefully guided by a specific parametric model, we could converge faster. The generative model could converge faster.
I think nowadays kernel is no longer a good choice because you only care the overall distance or dissimilarity or similarity
between distribution. Exactly.
You don't care each. Well, what's the meaning of each feature?
Exactly.
That's why I don't like. I don't say I don't like kernel, but I don't like distance.
I think you don't like distance.
Yeah, I don't like distance-based learning method at all.
I see. Sorry, why is that?
Yeah, because by computing the distance and then or by computing similarity or dissimilarity, basically you only care some summarized information from all the features, and you don't care each feature.
I see.
Basically, you lose of your representation learning ability.
I see.
But here, basically, I think you don't update the app at all.
No, I don't update the app at all. But actually, one thing I was, I didn't have time, but I was trying to do was to actually pre-train an F on some data set. Probably, like for example, using, score matching for some energy-based models, then we, discard the last layer and then use the, penultimate layer as the f of x. So that hopefully like that choice of F would capture all the features that you mentioned, like all the, representation of your data set.
So part 3, if you only have some very small limited data set,
Right.
you don't have a way to learn. You have to retrain it, right?
Yeah, that's a good point. That's a very good point. Yeah.
Also, because you are doing parametric statistics,
Yes.
I always have such a question: how do you know your model is correct?
Yeah, that's a good point.
Because I have this idea, you assume some time varying small function.
Right.
And you assume that you only need to change the last layer, or like a theta t.
Right.
Theta depends on t, but f does not depend on t.
Right.
Why? Because you assume that f is very powerful. It's like foundation.
Exactly. Yes.
You only need to let theta to be dependent on t.
Exactly.
But f does not depend on t. But that means your underlying distribution, like t x represented by theta t,
Yeah.
is very smooth over t.
Yes.
It's not. relatively smooth over T, but it's not a very smooth over T. Then you need to also let
Right.
maybe the second last layer, the second.
Yes, yes, exactly.
three layers to be
Exactly.
depend on T.
Exactly, yes.
Your theory or maybe your duration of the algorithm only allow, okay.
Last
the
layer.
last layer depend on T, and then all the remaining layers do not depend on
Yes,
T.
exactly. Yes, yes.
You know that your model is correct.
Yeah. That's a very good point. That's a very good point. I'll definitely take this into account. Yeah. So we are trying to derive some kind of theory.
And also for like the model selection.
Right,
You have
right,
the
right.
linear model and the Fourier model.
Right,
And then
right.
say, okay, we use our eyeball to see what change it is, and then we apply a model.
Yes.
There is no way to maybe say cognitively select whether I should use the linear model or the Fourier model.
Yes. That's a good
And
point.
maybe later you will have the third model, the fourth model.
Yes,
So you
yes.
should have a way to select.
Model selection. Yes, absolutely. Yeah, these are very interesting comments. Yeah, absolutely.
Yeah, but if you are doing discriminative learning, you don't have such.
Right. I see. Interesting. Yeah. Sorry, did I run over time?
Yes, maybe you can just quickly go through the.
Oh, I don't have any.
Okay.
I think.
There's one more question?
Oh, yeah, I replied to them.
Yeah. So basically, this is the end of the talk. Like the last result is the result of the covariance shift, and that's the conclusion of the talk. Yes.
Okay, thank you so much for the nice talk.
Yes.
Due to the limited time, maybe we can have one quick question. Or is there any question? Or yeah, I think there's no question. Maybe I have one quick question.
Sure, of course.
Do you think how to extend your method to some abrupt change?
Abrupt change.
Yeah.
I see. That's a good point. So in our case, we only assume the theta t to be smooth.
Yes.
Because that is required when you take differentiate the partial t theta. Otherwise, the derivative doesn't exist.
Yeah.
However, we were also thinking about an algorithm to do change point detection, because essentially we could perform some kind of statistical test, like Gang said, that whether the assumption on the smoothness of theta t is satisfied. If it is not satisfied, based on some statistical test, then we could declare a change point in a time series.
Yeah, I think the main question maybe is how to define the criteria to detect the change. So what do you have any?
For example, like I could consider some kind of test statistics that is the magnitude of estimated partial t theta t. So of course, like if there's a sudden spike theta t smooth, then a jump, then you'll see at this change point the partial t theta t goes blows up to a very large number. So then I could declare a change once I see the magnitude of estimated partial t theta t beyond the threshold.
Okay, thank you very much.
Yes.
Practically speaking, you can just check the performance or the loss of this method.
Yeah, exactly.
So assume something, and you know that if the assumption is correct, it will
minimize. Yeah.
And then you put, oh, this method doesn't work now.
You're the change point. Yes.
Yeah.
Exactly. Yes.
Yeah, but how to set the threshold may be a good.
Yes, the threshold. Yeah.
It's really hard to set, I think.
Right. So that's what I think we could derive some kind of statistical asymptotic properties and then look at null distribution and set the threshold there. Yeah, that's true. Yes.
Thank you.
One more kind of high level.
Yes.
So maybe it's similar to what Carl said.
Yes.
Only internal changes over time.
Right.
The inner product is the counterpart of this.
Yes, exactly. Yes.
Then you for example, work on test time adaptation.
Right.
You also try to update the feature extraction part.
Exactly. Yeah.
And somehow take into account that kind of flavor.
Actually, this is a really interesting question. I have already tried some results. So for example, in the last part, I was training the generative model. It's really hard to find a powerful F to train a good generative model. So what I thought was, okay, in my algorithm that you see, there's a loop here. So each iteration, I do all these things. So basically I add another step that is, training a new F. So essentially in that case, as I am evolving the generative model, I'm also training, a sufficient statistic over time for each different t. And the results seem to work really well. for example, at time point t, I could just train, FT using some like a score matching with energy-based model, and it seems to work really well. So I think if we are considering this kind of time varying fashion, so in my opinion, is like this is only the first step, and the next step, definitely including the time dependency of f, is a great way to improve the expressiveness of f of x over different time t, because it could be like for the first half of the time series this f is better, but for the latter half the other f is better. So I think if we could derive this kind of like updating mechanism for f over time, it would be very useful for many applications. Yeah.
Thank you for the next question. So if there's no more question, I think maybe this is the end of this seminar. Yeah, thank you so much for the next talk.
Thank you, Jeff. Thank you for the question. Thank you.